Today, on how it's made. Engine blocks. We take a trip to the hood. Jawbreakers. Workers at this factory take their sweet time. Drum shells. We'll round out all the details on how they make them. And drums. We really get into the beat with this story. The engine block is the largest single piece of metal in a car, and also one of the most intricate. It houses and links all the engine components, such as the cylinders and pistons, and it contains passages for circulating coolant. The engine block is where combustion converts into mechanical energy that drives the transmission, propelling the car. Engine blocks used to be made of iron. Today, most are made of lightweight aluminum alloy for fuel efficiency. An engine block is a one-piece component cast from a sand mold. To make the mold, the factory mixes glue and a hardener with zircon sand. This combination of materials can withstand the intense heat of molten metal, but only for one casting. Each mold is made up of sections called cores that fit together. To make each core, a machine blows the sand and glue mixture into a master mold made of iron. It injects a gas that activates the hardener, which solidifies the mixture. This is the base core to which the other cores will attach. The base core travels down an assembly line to receive the other cores. The next core molds the engine block's cylinder bores, which will house the motor's pistons. A robot inserts iron liners into 6 holes in the core. They prevent the aluminum walls of the bores from wearing out from abrasion. The base core receives 17 other cores. The ones for engine block areas through which oil will flow are coated with talcum powder. This keeps sand particles from sticking to the aluminum and getting into the oil. The machines glue certain cores so they'll stay intact when the robots flip them upside down and attach them to the rest. These are the last 2 cores. The mold is now fully assembled and ready for casting. Workers load aluminum ingots into a device called an elevator bucket. It positions them above the jet melter, a gas-fired furnace. The bucket drops the ingots into the 800 degrees Celsius fire, liquefying the aluminum. Just before casting, they heat the cylinder bore liners using high-frequency electric current. Aluminum will bond better to hot metal. They fill the molds from the bottom to avoid contaminating the metal with aluminum oxide. Oxide forms when molten aluminum comes into contact with the air. Pouring into the top of the mold would expose the metal to oxygen, and the pouring action itself would mix in the oxide. After the casting, the molds spend 6 hours in what's called a thermal sand reclaim oven. That breaks down the glue so the sand falls away. The heat also strengthens the metal. The cast aluminum engine blocks emerge, needing just some minor finishing. Robots turn them upside down to spill out loose sand. Machines saw off the risers, extra metal that fed the mold cavity to compensate for the 7% shrinkage that occurs when liquid aluminum solidifies. Finally, computer-guided tooling equipment performs a rough machining of the metal. This brings the engine blocks to a near-finished state. The engine plant that buys them does the final machining before installing the engine parts. Every engine block this factory produces passes through an automated vision system that inspects the engine blocks to ensure they have no defects whatsoever. Jawbreakers, also known as gobstoppers, have preoccupied candy lovers for decades. You pop one in and slowly suck or chew through up to 10 layers of colors and flavors. Sometimes there's bubble gum in the middle for an even longer lasting finish. The larger ones are just for show. Most jawbreakers are about the size of a golf ball. To make their bubblegum centers, a worker blends synthetic rubber with powdered resin, which will dissolve the rubber. He adds a thickener, a preservative, and an oil called soya palm stearine, so the candy won't stick to your teeth. After mixing and steaming at 148 degrees Celsius for 4 hours, the batter pours into trays to cool. Sugar, coloring, and flavoring would deteriorate in the heat, so workers add those later. There's enough of this base to make gum centers for 450,000 small jawbreakers. After 24 hours, the batter's hard. Workers chop it up and blend it with corn syrup to make it softer and sweeter. They add 45 kilos of finished gum that didn't make it into jawbreakers before because it wasn't the right shape. Now they add natural and artificial flavors, which can include lemon, orange, strawberry, grape, and even tutti frutti. Then they add icing sugar. It makes the gum smoother to chew than regular sugar would. Workers dump the batch into an extruder that shapes 2 continuous streams of batter called rope. Another extruder divides each rope into 6 hollow tubes. The cavity inside will become pockets of air inside the gum centers. The next machine slices the tubes into 1 meter long segments. A mechanical arm pushes the segments into the channel of a forming machine. Steel rolls then slice through the tubes and shape them into balls. The balls range in diameter depending on the size of the jawbreakers being produced. Air blows through perforations in a cooling tunnel to cool and firm the centers. Then they fall onto another forming machine, which restores their round shape. Other jawbreakers have hard candy in the center. The machine that makes them works like the presses drug companies use to make pills. It feeds candy powder into dies, then applies up to 5 tons of force to compress the powder into a solid candy. Now for the rest of the jawbreaker. First, they dump the candy centers into what's called a coating pan. They add a hot mixture of water, corn syrup, and food coloring. Then dextrose, a type of powdered sugar. The pan rotates for 20 minutes as warm air dries the ingredients over the centers. The factory repeats this step 10 times for each layer. Talk about a sweet ordeal. Making a jawbreaker takes 4 days. Workers give this batch special treatment. They speckle these jawbreakers with different colors, giving them what this company calls the psychedelic look. After letting the candies dry for 24 hours, a worker adds pinches of powdered carnauba wax. This gives the jawbreakers a shiny finish. Sliced open, you can see these jawbreakers have 10 layers of flavors and sugar surrounding either hard candy or bubblegum cores. They measure 5.7 centimeters in diameter, as big as a billiard ball. And if you're counting calories, forget it. A jawbreaker is 90% sugar. Almost every culture has marched to the beat of its own drum. Drums have been part of different civilizations for thousands of years. The earliest drum shells were hollowed-out logs or gourds. Different sizes created different sounds. Today, drum shells are a little more sophisticated, but the beat goes on. To make drum shells, they slice an enormous rock maple log into several boards. Maple is ideal for making drum shells because its hardness allows sound to resonate fully. Each of these maple boards will be transformed into one drum shell. Workers feed the boards to a ripsaw, which cuts them to the correct width. This varies depending on the size of drum being made. Then each board goes into a planer, which shaves it thinner. A worker aligns the board with markings on a saw table. This positions the board to be cut to the correct length. A radial arm saw does the job neatly. Now he sizes up each board in preparation for tapering. He places a board on an angle in a jig and then moves the end against a router cutter to taper it. It takes a few passes to get it just right. The taper needs to be about 15 centimeters long. He thins the other end of the board to the same dimension. These tapered ends will make it easier to bend the wood into a drum shape later. They'll also act as scarf joints, which will fasten the ends of the board together when it's bent round. But first, this board needs some softening up. An hour in the steam box does the trick. It's pliable enough to wind around a hot cylindrical form. Steel banding secures the board to the bending form, where it will spend 10 to 15 minutes. A worker pries apart the ends and applies a generous amount of glue between the tapered tips. Then he removes the shim that was holding the ends apart so that they stick together. He places a wooden guard over the glued joint. This nylon mesh band is a clamp. He wraps it around the drum shell and turns a screw to pull the band tightly around the wood until it reaches 35.5 centimeters in diameter. Then he fastens over a dozen steel clamps onto the joint. All these clamps will prevent any gaps from occurring in the joint as the glue sets overnight. With the joint sealed, the drum shell now spins while a cutter shaves down the edges to make it a true round shell. Then they bring in another cutter. It bores into the shell, making a smooth edge and rounding the inside. He turns the drum shell around to cut it from another angle. As the shell spins, a high-speed cutter shaves the outside from top to bottom. This makes the surface very smooth. It takes about a week to make a drum shell from solid wood, and it'll be able to stand up to a real beating. There's more than one way to beat a drum, and there's more than one way to make one. Earlier, we showed you how they create a drum shell from a maple plank. But a newer technique involves layering multiple plies of wood. This process is called laminating, and you can hear the difference. The laminated drum is an instrument of change. Its sound is crisper than a drum crafted from a single piece of wood. To make one, they layer 11 sheets of maple. Here, a worker glues on the final ply using a special adhesive. This outer layer is luxurious bird's eye maple. Rollers press all the layers together to ensure they stick without any gaps. Then they cut through the overlap to create a perfect seam. A robotic drill now takes over. It drills holes of various diameters. The small ones will hold hardware. This larger one is an air vent. A computerized router then cuts the bearing edges to a 45-degree angle, and a worker sands it smooth. He uses a level surface to ensure that all the edges are perfect. If they're not, the drum heads won't fit properly. He applies an adhesive to the air hole and inserts a plastic vent. Next, he inserts brackets called lugs into the other holes and screws them in. There are 10 lugs, spaced 36 degrees apart. They'll hold the rods that will attach the heads to the drum shell and also enable the drummer to adjust the tension on the heads. Here, he attaches a lever to control wires called snares that are to be strung across the bottom head. It's called a snare strainer. Then he fits a plastic drum head over the bottom of the shell. The counter hoop goes on next. It has little tabs, which he aligns with each lug. He slides tension rods into the holes in the tabs. Using a drum key, he tightens the head to an even tension across the shell. Now he blasts it with a heat gun to shrink the plastic and remove any wrinkles. Now he places another plastic head on the top bearing edge. Since this head is the one that gets pounded on, it's twice as thick as the bottom one. He places the chrome rim on it and tightens the tension rods. These brass brackets will hold the snare wires. He slides them under the snares that are stretched tightly across a jig, putting one at each end. He measures the length, then solders the snare wires to the brackets. He snips the wires on both ends and unlocks each wire from the holding device. When he removes the snares, they're held together by the brackets. He slides a nylon strap into one of the brackets, then attaches the strap to a fixture just above the bottom head. The other end of the snare is attached to the strainer, the lever that will apply tension and release it, controlling its distinctive buzz. For a bigger sound, there's the bass drum. It's made with wooden hoops. They attach the hoops to the drum shell with steel claws. As they screw the claws to the hoop, the drum head is pulled just tightly enough to produce that low-pitched bass drum sound. A sound production indeed. Today, on how it's made. Glass bottles. Clearly fascinating. Hacksaws. We're off to a tool factory that's a cut above. And goalie masks. Making them is a face-saving endeavor. Whether they're colored or clear, glass bottles and jars are green. No trees die to make this eco-friendly packaging. Glass is made of natural ingredients that are abundant. You can recycle glass endlessly, and making it uses less energy than producing metal or plastic. The recipe for glass combines about half a dozen natural raw materials, but the main ones are silica sand, soda ash, and limestone. Silica sand usually makes up about 45% of the batch. The soda ash helps melt the silica evenly. It comprises about 15%. A limestone content of about 10% makes the finished glass more durable. They combine these ingredients with recycled glass called cullet. The factory's equipment feeds precise amounts of the materials into a furnace. Over a full day, the fiery heat, 1500 degrees Celsius, melts everything together, producing a gooey liquid that's the consistency of honey. The molten glass pours out of the furnace. Shears cut the flow at precise intervals to produce cylindrical gobs. Each gob is the exact amount required to make one bottle or jar. They drop to a device called the scoop. The scoop moves them to troughs that feed them to jar and bottle forming machines. A gob of molten glass goes into a preliminary mold. In a matter of seconds, it comes out as what's called a parison, a miniature version of the final bottle. Each parison then moves into a blow mold, the cavity of which is the shape of the final bottle. The equipment blows compressed air into the parison, stretching the glass outward towards the wall of the mold cavity. This process creates the final bottle shape and hollows out the inside. These are amber-colored beer bottles. The color is produced by adding small amounts of iron, sulfur, and carbon to the glass mix. The factory uses a similar manufacturing process to produce other types of bottles and jars. In this run, the company is making 375 milliliter wine bottles out of clear glass. This run is producing 375 milliliter liquor bottles, also out of clear glass. But this mold has a special feature, a recessed insignia on one of the walls, which produces a raised insignia on the front of the bottle. After the bottles leave the forming machine, they travel through flames. Otherwise, they would cool down too quickly and crack from thermal shock. A loader now gently pushes the bottles into what's called an annealing leer. The bottles cool at a controlled rate as they move through the leer. This releases stress from the glass gradually. As the bottles exit the annealing layer, a sprayer coats their exteriors with lubricant. This enables them to move smoothly through the rest of the inspection and packaging line. The bottles now line up in single file to head into the automatic inspection station. As the machine spins each bottle, cameras and probes check for imperfections such as cracks or bubbles. The inspection equipment then examines the top to check dimensions and ensure the threads for the screw cap are molded correctly. Before shipping, a worker does a final visual inspection. The proportion of cullet in glass can be as high as 90%. Cullet melts at a lower temperature, so for every 10% of cullet in the mix, the factory uses up to 2.5% less energy to produce its glass. Now that's an incentive to recycle. The world of saws is made up of many marvelous tools. Big saws and jigsaws, handsaws and bandsaws, bagsaws and hacksaws. They all have their specific purpose. Hacksaws are chiefly for cutting metal or other tough materials. So what keeps hacksaws on the cutting edge? Hacksaws come in many shapes and sizes. Companies make hacksaw blades out of a wide range of steel alloys. Here, a thin band of steel feeds into a machine that cuts it into blanks 25 to 30 centimeters long and 1.3 centimeters high. Workers load 300 blanks at a time into a jig. They lightly hammer them to compress them into a block for easier cutting. They then feed the block into a machine called a mill grinder. It cuts teeth into the upper side of the blanks. A water-based lubricant washes away the metal particles. This hacksaw model has a 24-point blade, which means there are 24 teeth to every inch or 2.5 centimeters. Workers use an ordinary paintbrush to remove any metal residue. The quality control department inspects each blade for flaws. Then it's off to the next phase. A separator detaches each of the 300 blades, aligns them, then sends them through a setting machine. The machine bends the teeth to either side at a slight angle. This is called offsetting. It'll enable the blade to clear away particles as it saws, preventing it from jamming. Now it's time to harden the teeth. The factory does this by heat treating the metal. A worm gear aligns the blades to enter a heating coil. In this process, the electromagnetic heating coil heats the teeth to temperatures as high as 1200 degrees Celsius, depending on the type of metal. This takes no more than 2 seconds. After the blades exit the heating coil, the surrounding air cools them down over the next several hours. This phase is called air quenching. The blades are now ready for printing. An offset printing press applies ink to raised lettering on a cylinder. That cylinder transfers the ink to strips mounted on another cylinder. These strips then print the company name, the blade length, and the number of teeth per inch on the side of the blades. Now a machine inserts the blades in groups of 5 into slots called fingers. The fingers rotate the blades and place them on a conveyor belt. The machine raises the blades and tapes them together at one end. This makes it easier to transport them to another part of the factory, where production continues. Next, the hacksaw's frame, the component that holds the blade. Workers place the frame components in a jig that's positioned on a rotating carousel. A robotic welder fuses the components. A press punches 3 holes in the handle for attaching a foam or plastic grip. Workers fit the 2 halves of the grip in a sonic welder that fuses them using high-frequency sound waves. The sound waves create friction at the seam. This generates enough heat to melt the parts together. Now the frame is ready for the blade. An automatic device tightens a wing nut to put tension on the blade. A final quality control check. With each randomly selected blade, the testing machine cuts through a block of stainless steel. The machine performs this test 6 times per blade. Then the computer calculates the average number of strokes. If that average falls within the norms for this particular model, the batch gets the thumbs up. Keeping those thumbs, of course, clear of these sharp tools. Goalie masks are all about putting up a tough front. It's not just their protective shell and cage, their wild paint jobs are designed to intimidate. Incredibly, back in the 1960s, the first masked goalies were ridiculed by fans who viewed the masks as a sign of weakness. It was a case of adding insult to injury. Today, these masks allow the goaltender to play it safe, so they're far less likely to be sidelined by a serious injury. They start with a plaster mold of an average Joe. They plug the mouth hole with plasticine. This ensures that the mold won't spring any leaks while they fill it with plaster of Paris. They let it dry for half an hour. Then they pull off the initial mold to reveal the solid impression. They press plasticine onto strategic areas. This mimics the foam safety guards that cushion every mask. The final result is called a plug, and it will be used to make a 2-part compression mold. After applying a black sealer, they polish it smooth, eliminating imperfections that would be visible on the mold they're going to make from it. Over at another station, a worker in protective garb unrolls fiberglass fabric. He cuts and layers sheets of it, then draws patterns onto the top one, spacing the shapes closely together to minimize waste. The goal is to score 100 goalie masks from one roll of material. Using a disc cutter, he slices through 25 layers of the fiberglass fabric. Then he stacks various composite fabrics, several of the fiberglass ones, and patches of Kevlar for reinforcement. Kevlar can absorb so much impact, it's also used to make bulletproof vests. He places more fabric over the Kevlar. He spreads an epoxy resin onto each layer. He drapes them over a mold that's been made from the plug and smooths the material to eliminate air pockets as he continues to layer and glue. He's laminating all the pieces together to form one. He trims away the ragged edges and then places the inside portion of the mold into the outside one. The wet fabric is now sandwiched between the 2 mold pieces. He lowers a 1-ton press to compress the layers of fabric as the resins between them continue to form a bond. He adds some clamps to keep things tight. After 20 minutes, he pries the laminated fiberglass shell out of the mold. This is one very tough shell. It's the raw form of a goalie mask, but it still needs a lot of work. So it's over to the trimming and grinding station. He places a trim jig over the shell. Using a high-speed router, he cuts an opening for the cage. He slices off the flash with a disc grinder. And then he sands and grinds the edges. He drills holes to attach various fasteners. Then he carves out larger holes for ventilation and to reduce the mask's weight. Coming up next, watch as the paint pros go to work on these shells. The makers of goalie masks have turned safety into an art form. The goalie mask has become a canvas for some very bold designs and colors. It's a kind of psychological tactic to intimidate the other team, and it also scores points with the fans who like the cool paint jobs. They prep the mask by roughing it up with an orbital sander. Then they pour a sealer into a container. The technician wears a charcoal respirator because the emissions are toxic. He adds the activator solution and a reactive reducer and stirs the sealer together. Then he sprays the sealer mix onto the masks. The finish will cure and harden as the chemicals in it generate their own heat. Next, this system stirs up some hot hues automotive paint as the technician sprays a vivid gold base coat onto the masks. Computer graphics created with SignLab software are sent to a plotter that cuts out adhesive vinyl paint masks. He pulls away unneeded vinyl around the stencil, a process called weeding. Then he presses the vinyl stencils against the goalie mask and peels off the paper backing. Applying a stencil to the crown is tricky because the surface is curved with ridges, so it doesn't lay flat. He lifts and cuts the pattern with a utility knife and then straightens it out. This mask is starting to look pretty impressive. But they cover the whole thing with white paint. It's a temporary cover-up. This process is all about layering patterns and color. They apply more vinyl shapes. And then, using a pressurized paint system, they spray everything bright red. Next, an artist airbrushes some shadowing onto the now barely visible image of a leaf. He peels away some of the paint mask vinyl. And it's time for a really neat effect. He sprinkles the surface of the mask with water. Then he mists it with paint, and the water droplets catch the paint. He blasts it with a heat gun. The water evaporates, but the paint dries in droplet form, giving the mask a frosty look. He airbrushes a drop shadow around some lettering, dispensing with the usual safety gloves for this detail work. And now, all is revealed as he peels away the vinyl. The goalie mask is showing its true colors. But wait, a little touch-up job is needed. He traces the pattern onto see-through paper and then transfers it onto Bristol board. He cuts it out with a utility knife. Then he aligns it with the shape on the mask and precisely airbrushes around it to make the smudge disappear. With the final clear coat, this mask has visual impact. It makes a colorful statement. And now it's time to put all the pieces together. She screws on the stainless steel cage and applies a little glue to reinforce the adhesive-backed foam cushioning. She attaches the sweatband with Velcro so it can be removed and washed. And then she moves on to the back plate. She threads the harness through the back plate to the front of the mask to attach them. The harness is elastic, so it gives the mask some flexibility. And now, it's ready for some ice time. With their various custom paint jobs, these masks all say, "The puck stops here."
Today on How It's Made. Firefighter boots. What's hot in footwear? Garden tools. You'll get the facts in spades. Automated machines. Our annual tribute to those moving marvels. And gypsum board. We're giving this story wall-to-wall coverage. Firefighters need boots they can pull on lightning fast to get to the blaze as quickly as possible. Those boots have to be fire-resistant, of course, and waterproof. They have to provide good grip for climbing ladders and be sturdy enough not to puncture when stepping through sharp debris. Firefighter boots start out as a chunky block of rubber. The first step is to put the block through a mill. It passes through the rollers over and over again until it gradually flattens and thins out. Workers then add chemicals, anywhere from 15 to 35 different types, depending on the model of boot they're making. The rubber formulation is what makes the boot fire-resistant. Once the rubber is smooth and malleable, about the consistency of modeling dough, they form it into sheets from which they'll cut the various pieces that make up the boot. They feed this sheet through rollers that imprint vertical lines on the rubber. They'll cut the sheet along these lines to make the strips that run down the back of the boot. From another sheet of rubber, using a handheld die, they cut one layer of the multi-layered sole. They run an extra thick sheet of rubber through rollers that imprint a tread pattern. Then workers cut out the bottom soles. They mark the boot size on the bottom. Using yellow rubber, they cut out the boot's toe cap covers. The boot's leg has a stiff lining to prevent it from wobbling. Workers cut it from a rubber-backed cotton fabric following a pattern. Once all the pieces are cut, workers can assemble the boot on a form. They start with the lining, wrapping it around the front and gluing it closed at the back. Then they glue on the insole. For this model, it's made of rubber-backed felt. They secure the lining seam and seal it with one of those rubber strips we saw earlier. Now, the vamp, a piece of felt reinforced with a thin layer of rubber. This gives the boot strength. Next, the toe cap sponge, made of rubber compounds. When they cure the boot, the sponge will inflate and hold this steel toe cap in place. To protect the firefighter's feet when walking through sharp debris, a steel arch and a steel sole. Next, an adhesive-backed toe cap cover. Then a felt sole to protect the firefighter's foot against heat. It has a steel arch for stability when the firefighter climbs the ladder. After applying a rubber heel reinforcement, they cover the lower part of the boot with yellow foam for insulation. They secure it using a strip of rubber. Now they finish the bottom of the boot in black rubber. They reinforce the back and sides in yellow rubber and finish them off in black rubber. Next comes the yellow toe cap. Then a rubber pad to protect the front of the boot when it rubs against the rungs of the fire ladder. Now the bottom sole. They use a press to seal it in place. Rubber bonds to rubber under pressure. They apply a rubber trim around the bottom, using a small roller to press it in place. Workers then press all the seams to ensure they're well adhered. Then it's into a vacuum machine for about 4 seconds to create an airtight bond. Finally, the boots go into a giant oven that heats them to 140 degrees Celsius. An hour and 45 minutes later, the rubber is cured and hardened, and all the pieces have fused together. These boots are ready to take the heat. Anyone with a green thumb knows that it takes both skill and patience to make a garden flourish. It also helps to have the proper tools on hand. An avid gardener's arsenal can contain everything from shears, trimmers, and pruners to rakes, hoes, and spades. The handles of these garden tools are made of white ash, a sturdy wood that can withstand the force of shoveling, digging, or raking. These dried ash dowels measure 1/2 meter to 2 meters long, depending on the tool being made. They first enter what's called the chucking line, where specially designed automated machines shape them into handles. The first operation rounds the dowels to the required diameter, 4 centimeters or so, depending on the tool. The next operation cuts the dowels to the required length and profiles their ends. Two chucking heads, one on each side, carve the ends simultaneously. One shapes the bottom of the handle to fit the tool's blade. Certain blades go over the wooden handle while others go into it. For those inserted blades, another chucking head hollows out the handle. Meanwhile, the chucking head on the other side rounds off the top of the handle. The finished handles spin against a sanding belt as they exit the chucking line. This smooths the surface of the wood, preparing the handles for a coat of protective varnish. High-end shovels and spades have what's called a steel D-grip, a steel handle grip with a wooden insert. An automated lathe first shapes a piece of ash to the right length and profile. Then an automated drill pierces a hole. To make the sides of the grip, workers begin with 2 pre-cut pieces of steel called blanks. They place them in a manually operated press that shapes them in a 2-step process. They use the heat of a strong electrical current to melt the steel and fuse the pieces together. This is called resistance welding. Next, they feed a steel rivet through the sides and wooden insert and fasten everything together. Elsewhere in the factory, meanwhile, a heated forming machine stamps out the steel blanks that workers will shape into blades. A robotic arm loads the blanks into an oven. In a mere 4 minutes, the oven heats the steel to almost 1,000 degrees Celsius. This intense heat makes the metal malleable. Workers then take out and shape one blank at a time. They have just a few seconds to form the steel before it cools off. The first press forms the blade, in this case a shovel, and a partial socket. Then the second press closes the socket. They quickly submerge the blade in lukewarm water to cool the metal down. By now, the steel is extremely brittle, so the blades go into what's called a tempering furnace for 15 minutes. This alters the metal's internal structure, restoring its strength. The steel D-grip, meanwhile, has been cleaned and painted. Workers insert the wooden handle and nail the parts together. On the other end, they attach the blade, which by now has been varnished to prevent corrosion. After drilling a hole through both the metal and the wood, they fasten the blade using a rivet if it's a high-end tool, a nail if it's a budget model. These hot-off-the-press garden tools are finally ready to put in a hard day's work. A couple of centuries after the Industrial Revolution, mass production met automation, a match made not in heaven, but in high technology. In this special segment, How It's Made honors the automated machine with this moving tribute. called gypsum board or drywall, and chances are your walls and ceilings are made of it. Years ago, it replaced plaster as the wall material of choice. Workers just mount the sheets onto wood framing, plaster the joints, then sand and paint. Gypsum is a natural mineral. Since ancient times, it's been mined to produce gypsum plaster. In fact, there's gypsum plaster in Egypt's pyramids. In 1894, a man by the name of Augustine Sackett patented a board made of gypsum, which he called plasterboard. But it didn't become the norm in construction until the building boom that followed World War II, when busy contractors abandoned plaster in favor of this faster and cheaper way to build walls. The process of making gypsum board begins at the quarry, where crews mine the gypsum, a soft rock. The loaders dump their haul into what's called an apron. The apron channels the gypsum onto a conveyor, breaking up the big chunks along the way. From there, it's into a giant rotating drum. Within 8 minutes, this hot air rock dryer removes 5 to 10% of the moisture, turning the gypsum white. Next stop, a gas-fired silo called a kettle. It cooks the gypsum at 150 degrees Celsius until most of the remaining moisture evaporates. Feeding that kettle, a mill that grinds the lumpy rock into what's called stucco, a fine powder the consistency of wheat flour. In a mixing tank, meanwhile, workers combine water with several powdered chemicals and minerals and a chemical soap. The dry additives give the board the required structure, while the soap creates air bubbles to make the board lighter. In a separate machine, they mix the stucco with an accelerator to make the gypsum set faster. Now they combine the two separate batches, creating a mixture called a slurry. It looks like thick white soup. Now they'll form it into gypsum board, which is basically a slurry sandwich. The bread is this thick, heavyweight paper. As the roll unwinds, creaser wheels, as they're called, score a line about 3 centimeters in from both edges. Then a machine evenly spreads the slurry, like a sandwich filling, between the top and bottom sheets of paper. Then the paper folding operation, most of which is a company secret and off limits to our cameras. They fold the edges along the score lines, the bottom edges upward, the top ones downward, gluing them over the bottom ones to trap the slurry inside. Drops of water smooth out any ridges, ensuring a smooth and even fold. Forming plates then shape the folded edges into straight sides. An optical sensor checks the depth of the board's recess. That's where you put the joint tape to connect one board to the next when you're building a wall. The forming station spews out 305 continuous meters of gypsum board at a time. A cutter now chops that mega board into whatever length board they're producing in this run. As the boards exit the cutter, automated prongs flip them recessed side up. Since the recessed side will be the wall surface, they don't want to risk damage by having it travel face down on the rollers that lead to the drying station. This gas-fired hot air dryer is kind of like a multi-level parking garage. It's more than 150 meters long and has 8 decks. The factory can cure hundreds of boards at a time. It takes 40 minutes to move through the dryer's 4 temperature zones, which start at 350 degrees Celsius and get progressively cooler to 150 degrees. The boards are sold in pairs, so the machinery stacks them in twos, then tapes them together. The tape bears the brand name as well as the size and thickness of the board. Standard lengths range from 8 to 14 feet. and the most common thicknesses are 1/2 inch and 5/8 of an inch. In this industry, imperial measurements are still the norm. The tape also tells the consumer what type of gypsum board it is. There's standard drywall for building walls in homes. There's a moisture-resistant version for humid areas such as bathrooms. There's also fire-resistant gypsum board, usually required by law for commercial buildings.